Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The breath of Earth, unveiling the secrets of our atmosphere. The Earth's atmosphere, a dynamic and complex layer of gases enveloping the planet, serves as a critical component of Earth's systems, enabling life and shaping weather patterns. Composed primarily of nitrogen, 78%, and oxygen, 21%. With traces of argon, carbon dioxide, and other gases, the atmosphere is a shield and sustainer of life. It regulates temperature, protects against harmful solar radiation, and allows for essential processes such as photosynthesis and respiration. This multilayered structure is constantly in motion, driven by both solar energy and Earth's rotation, creating patterns that govern climates and ecosystems. At its core, the atmosphere's composition reflects the planet's history and evolution. Billions of years ago, volcanic eruptions released vast amounts of gases, forming a primitive atmosphere dominated by water vapor, carbon dioxide, and methane. Over time, biological processes like photosynthesis transformed this mixture, enriching it with oxygen and reducing carbon dioxide levels. This oxygenation event was pivotal, enabling the development of complex life and giving rise to the modern atmosphere. While this transformation unfolded over millions of years, it underscores the intimate link between Earth's atmosphere and its biosphere. The atmosphere is stratified into 5 principal layers, each with unique characteristics and functions. Closest to the Earth's surface is the troposphere, where weather phenomena occur. This layer extends up to about 12 kilometers and is marked by a decrease in temperature with altitude. Above it lies the stratosphere, home to the ozone layer, which absorbs harmful ultraviolet radiation. The mesosphere, extending further upward, experiences a dramatic drop in temperature and burns up meteors entering Earth's atmosphere. Beyond this lies the thermosphere, characterized by rising temperatures due to solar activity, and the exosphere, a transitional boundary to outer space. The troposphere, where human activity predominantly takes place, is a stage for an intricate dance of air masses, pressure systems, and moisture. Solar radiation heats the Earth's surface unevenly, causing air to rise, cool, and condense into clouds. This interplay of heat, moisture, and wind drives the water cycle, distributing fresh water across the planet and sustaining ecosystems. However, human-induced changes, such as greenhouse gas emissions, are altering these natural processes, leading to shifts in weather patterns, extreme events, and long-term climate changes. Beyond its physical dynamics, the atmosphere is a medium of interaction between the Earth and cosmic forces. Charged particles from the Sun interact with the Earth's magnetic field and atmospheric particles, creating phenomena like auroras in polar regions. These displays are a visual testament to the invisible processes that shape our planet's interaction with the broader universe. Similarly, the atmosphere acts as a filter, blocking out most of the harmful radiation and cosmic debris, ensuring the stability and continuity of life on Earth. The study of the Earth's atmosphere is a continuous endeavor, revealing its complexities and vulnerabilities. From understanding the delicate balance of gases that regulate temperature to the feedback loops driving climate change, the atmosphere remains a focal point of scientific inquiry. As the challenges of human impact grow more pronounced, the atmosphere's role as a life-sustaining shield becomes ever more apparent, urging humanity to steward this vital system with care. The Earth's atmosphere is not a static entity but a dynamic system undergoing constant change due to natural and anthropogenic factors. This system's interactions with solar energy drive weather patterns, influence ocean currents, and regulate the global climate. Within the troposphere, solar energy is absorbed by the Earth's surface, heating the air and setting convection currents in motion. These currents, coupled with the Coriolis effect caused by Earth's rotation, create wind patterns that distribute heat and moisture globally, forming climates and sustaining ecosystems. The stratosphere, situated above the troposphere, is home to the ozone layer, a critical shield against harmful ultraviolet (UV) radiation. Ozone molecules absorb UV radiation, converting it into heat and creating a temperature inversion that stabilizes this layer. However, human activities, particularly the release of chlorofluorocarbons (CFCs), have thinned the ozone layer, causing seasonal holes over polar regions. While international agreements like the Montreal Protocol have significantly curbed CFC emissions, the recovery of the ozone layer remains an ongoing process, illustrating the delicate balance between human activity and atmospheric health. Higher up in the mesosphere and thermosphere, atmospheric density decreases, and unique phenomena occur. The mesosphere, the coldest layer, plays a crucial role in disintegrating meteoroids through friction, protecting the Earth's surface from frequent impacts. In the thermosphere, solar radiation excites particles, creating high temperatures and phenomena such as the auroras. These shimmering lights are the result of charged solar particles interacting with Earth's magnetic field and atmospheric gases, offering a visual spectacle of the Earth's protective systems in action. The interplay between the atmosphere and the Earth's surface is particularly evident in the water cycle. Evaporation, condensation, precipitation, and runoff are processes fueled by the exchange of energy between the atmosphere and the Earth's surface. This cycle not only distributes water but also regulates temperature and shapes landscapes. Yet, human-induced changes, such as deforestation and urbanization, disrupt these processes, leading to altered weather patterns, reduced biodiversity, and increased vulnerability to natural disasters. Human activities also introduce pollutants into the atmosphere, altering its composition and functionality. Greenhouse gases, such as carbon dioxide and methane, trap heat, enhancing the natural greenhouse effect and driving global warming. This warming triggers feedback mechanisms, such as the melting of polar ice and permafrost, which release additional greenhouse gases, amplifying the effect. Moreover, aerosols, tiny particles released from industrial processes, volcanic eruptions, and wildfires, affect cloud formation and precipitation patterns, illustrating the interconnectedness of atmospheric processes. Understanding and mitigating these changes require a multidisciplinary approach that combines meteorology, climatology, chemistry, and environmental science. Advanced technologies, such as satellite observation and computer modeling, allow scientists to monitor atmospheric conditions, predict weather events, and analyze long-term climate trends. These tools are essential for identifying vulnerabilities, informing policy decisions, and fostering global cooperation to address challenges such as climate change, air pollution, and sustainable resource management. As research deepens our understanding of the atmosphere, it becomes clear that it is not merely a passive layer of gases but an active participant in Earth's systems. Its interactions with the biosphere, hydrosphere, and geosphere highlight the interconnected nature of our planet, where changes in one system reverberate through others. This interconnectedness underscores the importance of maintaining atmospheric health, not only for the sake of individual ecosystems but for the stability and resilience of the Earth as a whole. The Earth's atmosphere functions as a complex, interconnected system, intricately linked to both natural processes and human activity. At its uppermost boundary, the exosphere gradually merges with the vacuum of space, marking the tenuous edge of our planet's influence. Here, particles are so sparse that they rarely collide, but the presence of this layer highlights the atmosphere's gradual thinning and its role in shielding Earth from cosmic radiation and debris. The exosphere also acts as a gateway for human exploration, as satellites and spacecraft traverse this region, leveraging its thin gases to study Earth and the cosmos. The atmosphere is not only a physical barrier but also a dynamic medium for chemical reactions that sustain life and regulate Earth's climate. Key processes like photosynthesis and respiration rely on atmospheric gases, primarily oxygen and carbon dioxide, to maintain a delicate equilibrium. However, disruptions to this balance, such as the rise in carbon dioxide levels due to human activities, present significant challenges. Oceanic absorption of excess CO2, for instance, leads to acidification, which threatens marine ecosystems and, in turn, impacts the atmospheric carbon cycle. Atmospheric dynamics also play a critical role in sustaining biodiversity. The winds transport seeds, pollen, and spores across vast distances, facilitating genetic exchange and the colonization of new habitats. Migratory species depend on predictable atmospheric patterns to navigate and survive seasonal changes. Yet, the rapid pace of climate change is altering these patterns, forcing species to adapt or face extinction. This underscores the interconnectedness of atmospheric conditions and the biological world. Technological advancements have significantly enhanced our understanding of the atmosphere. Satellites equipped with sensors monitor changes in atmospheric composition, temperature, and pressure, providing invaluable data for weather forecasting, climate modeling, and disaster preparedness. These observations have revealed alarming trends, such as the acceleration of polar ice melt and the increasing frequency of extreme weather events, which are direct consequences of human-induced changes to the atmosphere. Efforts to mitigate these impacts are underway, emphasizing renewable energy sources, reforestation, and the reduction of greenhouse gas emissions. International agreements like the Paris Accord aim to unite nations in addressing climate change, reflecting the global nature of the challenge. Public awareness campaigns and educational initiatives further highlight the importance of individual and collective actions in preserving atmospheric health. Ultimately, the Earth's atmosphere is a testament to the planet's resilience and vulnerability. It has evolved over billions of years, adapting to changes while maintaining conditions suitable for life. However, its current state reveals the profound influence of human activity, reminding us of our responsibility to protect this vital system. The atmosphere's story is one of balance, complexity, and interdependence, a narrative that underscores the need for sustainable stewardship in the face of an uncertain future.